In the topic hydrogen and its compounds, previous lectures में मैंने हाइड्रोजन डायटोमिक मॉलिक्यूलर फॉर्म में जैसे एग्जिस्ट करता है उसमें उसके प्रिपरेशंस एंड प्रॉपर्टीज ये कवर अप किए हैं, और वाटर से रिलेटेड भी हमने एक कंसेप्ट इसमें कवर अप किया है, दैट इज अबाउट द कंसेप्ट ऑफ हार्ड एंड सॉफ्ट वाटर. नाउ वन इंपॉर्टेंट कंपाउंड ऑफ हाइड्रोजन, that is hydrogen peroxide, is to be covered up. Compound H2O2, that is hydrogen peroxide. The very first thing is about hydrogen peroxide is related to its method of preparation. How to prepare this compound? Let us talk about the preparation of hydrogen peroxide. One is from metal peroxides. One of the methods of preparation of hydrogen peroxide is from the metal peroxides. Especially the peroxide used for this purpose is barium peroxide. BaO2 is the formula for the peroxide of barium. Barium peroxide compound on reaction with sulfuric acid gives precipitate of barium sulfate and hydrogen peroxide. The precipitate can be filtered and the filtrate, that is hydrogen peroxide solution, can be obtained. Another method from metal peroxide taking the same barium peroxide is by using the acid orthophosphoric acid. Of course, there will be a difference only in this byproduct. We get barium phosphate along with hydrogen peroxide. Now in the reasoning questions, one thing is important here, that the preferred acid for the reaction is phosphoric acid. Instead of sulfuric acid, phosphoric acid is preferred in this method. Reason for this is the precipitation of barium sulfate is not complete since it is sparingly soluble, while the precipitation of barium phosphate is a complete precipitation because it is insoluble in water. Barium sulfate is sparingly soluble, so the small amount of barium ions, they are left with the hydrogen peroxide solution. Once again I repeat, we prefer phosphoric acid over sulfuric acid in this method of preparation. The reason is we would like to separate out the product of the byproduct, rather we should say, in the form of barium sulfate or in the form of barium phosphate. Now where lies the difference? The difference is in their solubilities. Barium sulfate is sparingly soluble while barium phosphate is completely insoluble in water. So complete precipitation and separation of barium phosphate can be done. Now what is the problem if we are not able to completely separate out the barium salt? The presence of barium ions along with hydrogen peroxide catalyze its decomposition. So to avoid the decomposition of hydrogen peroxide, to prevent the decomposition of hydrogen peroxide, we should separate out the entire barium ions present in the precipitate, in the solution. So barium ions can be only separated when they are in the form of phosphate, not in the form of sulfate. There is one more conceptual question, that whenever this reaction is used, we prefer only barium peroxide. Why? Because the corresponding salt formed either in the form of sulfate or in the form of phosphate, they can be easily separated by filtration. Suppose we consider that the metal peroxide is sodium peroxide. Had sodium peroxide been taken instead of barium peroxide, the product would be sodium sulfate. Sodium salts are all soluble in water, so those salts could not be separated easily. That is why we prefer barium peroxide instead of the sodium or any other metal peroxide. Now I come to one more important point. There is one more question based on reasoning part. Sometimes the question is asked about the nature of barium peroxide we use in this reaction. We should always prefer to take the hydrated form of barium peroxide, not the anhydrous form. The hydrated barium peroxide does not allow this precipitate to acquire the surface of barium peroxide. The hydrated form does not allow this precipitate to acquire the surface of barium peroxide. If we take anhydrous form of barium peroxide, then the precipitate so formed is adsorbed on the surface of barium peroxide, and that adsorption results into stopping down of the reaction. The reaction will not continue if the precipitate starts depositing on the surface of the barium peroxide compound. So these are the 2-3 points related to the preparation of hydrogen peroxide by using barium peroxide along with some acid. I repeat, which 2-3 things are important. Once again, we prefer phosphoric acid instead of sulfuric acid. We prefer barium peroxide instead of sodium peroxide. We prefer hydrated form of barium peroxide instead of the anhydrous form. This is one of the methods to prepare hydrogen peroxide. Now I come to the second method, that is from sulfuric acid. From sulfuric acid. This is a good method when hydrogen peroxide can be obtained by the electrolysis process. By the electrolysis process, we take sulfuric acid for the electrolysis process. The electrolysis process gives movement of two oppositely charged ions towards the two oppositely charged electrodes. At anode, in the electrolysis process, the anode is positive electrode. So at anode, the movement of anions start. Since the electrode is positive, negative ion will move towards the anode, and at anode, this negative ion will lose electron and the process of oxidation takes place. We get H2S2O8 along with the electron. Loss of electron is oxidation process. So this hydrogen sulfate ion undergoes oxidation to form this compound H2S2O8. I am coming to the details of H2S2O8. Before coming to that, let us talk about the things happening at the oppositely charged electrode, cathode. Cathode is the negative electrode in the electrolysis process. Cathode is the electrode where reduction reaction takes place. So H plus ions undergo reduction to form hydrogen gas. In an overall manner, the situation comes to be in the form of sulfuric acid after electrolysis giving hydrogen gas and H2S2O8, these two compounds. This is at cathode and this is obtained at anode. Now this compound H2S2O8, that is called as Marshall's acid. This compound, that is Marshall's acid, or we also call it peroxydisulfuric acid. So this peroxydisulfuric acid, when hydrolyzed means when dissolved in water, when reacted with water, it forms sulfuric acid along with hydrogen peroxide. Sulfuric acid along with hydrogen peroxide. So once again, hydrogen peroxide is obtained by the hydrolysis of the product obtained in the electrolysis of sulfuric acid. I repeat, in the electrolysis of sulfuric acid, the product obtained is Marshall's acid at anode, and this product undergoes hydrolysis to form hydrogen peroxide. So these are the two important methods by which hydrogen peroxide can be prepared. Now, related to its properties, we have to talk about the things in detail. So before coming to any other property of hydrogen peroxide, let us talk about its structure. Hydrogen peroxide, its structure. Here I draw the structure of hydrogen peroxide. In the structure of hydrogen peroxide, each of these two oxygen is sp3 hybridized. I repeat, each of these two oxygen is sp3 hybridized, and the oxygen atoms, each of the oxygen atoms are bonded with hydrogen atoms. One hydrogen is bonded with each oxygen. These two hydrogen are placed in such a manner that the structure of hydrogen peroxide is like an open book. This is said to be an open book like structure. Now how does it appear as open book like structure? It's very simple. See, since the oxygen is sp3 hybrid and it has two unshared electron pairs, therefore the two bonded atoms are in the angular or V-shaped arrangement. A similar thing with another oxygen. These two bonded atoms are in the V-shaped or angular arrangement. This V-shaped arrangement and this V-shaped arrangement, they collectively make the molecule in having the appearance like open book. These two hydrogen are placed at this kind of the two opposite ends of the book. If I am holding the book, open book, from these two opposite ends, so you can imagine these to be the position of the two hydrogen atoms. Now here we have the position of two oxygen atoms. So the two oxygen atoms are having single bond in between, and each of this oxygen is bonded with the hydrogen atoms, one with this oxygen, one with this oxygen. So this bond is considered to be the peroxide bond. Not only in this case, but whenever the two oxygen atoms are bonded with single bond in any structure, the bond is called as peroxide bond. Here also you can see this compound H2S2O8. This H2S2O8 compound has one oxygen-oxygen bond in the structure. This is the structure of Marshall's acid. So due to this peroxide bond only, it resulted into the formation of hydrogen peroxide in the hydrolysis reaction. So peroxide bond is what? Exactly, the peroxide bond is the single bond present between two oxygen atoms. Peroxide itself suggests the species O2 minus 2. This ion is called as the peroxide ion. Peroxide ion has bond order 1, that means the number of bonds between two oxygen atoms, that is 1, and the nature of peroxide is diamagnetic. Since there is no unpaired electron present in the peroxide ion, its nature is diamagnetic. You can also relate these conclusions, what I am saying related to the peroxide ion, with the theory given in bonding, that is molecular orbital theory. So following that molecular orbital theory also, you can come to the same conclusion related to the properties of peroxide ion. It has bond order 1, it is it is diamagnetic since there is no unpaired electron present in it. Right? Now, let us come to the detailed properties of hydrogen peroxide, the chemical nature and the other things. One thing should be noticed here, that hydrogen peroxide has again the polar OH bond. Since oxygen is much more electronegative compared to hydrogen, so due to the difference of electronegativity between the two, this bond is polar. Similarly, this bond is polar, so we get extensive hydrogen bonding in the structure. So hydrogen bonding will be a viscous liquid with high boiling point, but we should keep in mind about its easy decomposition process. Hydrogen peroxide is a sensitive compound towards decomposition, so it readily undergoes decomposition. I write the decomposition of hydrogen peroxide can take place in this manner. Even this decomposition is possible in very less favorable energy conditions. As such, the decomposition of any compound will be an endothermic process. The decomposition, the breaking down of the compound. But the energy required for this decomposition is so less that even the presence of sunlight, even the presence of some heavy metal ions, they start catalyzing, they start promoting the decomposition of hydrogen peroxide. So one precaution is taken there. At the time when hydrogen peroxide is to be stored, it must be stored in the colored bottles, so that the light will not be catalyzing or rather initiating this decomposition. And second, one more thing is there, hydrogen peroxide, if its decomposition is to be prevented, then some polyhydroxy compounds are usually added at the time of storage of hydrogen peroxide. I repeat, some polyhydroxy compounds are added at the time of storage of hydrogen peroxide. Now what exactly will be the role of that polyhydroxy compound? That polyhydroxy compound in hydrogen peroxide acts as a negative catalyst. A negative catalyst is that which decreases the reaction rate. So what exactly we want? We do not want hydrogen peroxide to undergo decomposition. So what we are expecting, hydrogen peroxide should be given a negative catalyst for its decomposition. So that polyhydroxy compound behaves like a negative catalyst for the decomposition of hydrogen peroxide. More about hydrogen peroxide, its concentration and the other things will be continued at the end of this part, but in between now let us talk about its chemical behavior. The chemical behavior of hydrogen peroxide, the chemical properties of hydrogen peroxide.